In ancient times, astronomers divided the stars into 6 classes according to brightness. The brightest stars were classified as first magnitude, the next fainter second magnitude, and so on. Here we see stars of 4th magnitude and brighter. Now we've added the 5th magnitude and the 6th magnitude. This is the region of the Big Dipper, with all the stars commonly visible to the naked eye. But with a small telescope, you can see 7th magnitude, 8th magnitude, and perhaps even fainter stars depending on the size of the telescope. Although we are not aware of it, the stars are moving and the pattern of stars changes continually. Let's see how these stars appeared to people very long ago. First, we'll mark the positions of the Dipper stars in 1975, and then shift them to positions back in 3000 BC. The positions have changed only very slightly since civilization began. So the constellations of ancient Egypt are virtually the constellations we see today. But let's watch the motion of these stars over a much longer period, say 100,000 years. The pattern of the Dipper is lost over 100,000 years. Now let's move back to the present time. This is called proper motion. All stars, including our sun, are moving through space with various speeds in various directions. The stars nearer the sun appear to move more rapidly than the distant ones. We'll see how astronomers can measure proper motion and the distance to the nearer stars in other parts of the sky. Here in the constellation of Lyra, the Harp, is the bright star Alpha. It's also called Vega. We'll look at Vega with a magnification of 30,000. With this much magnification, we should be able to see the proper motion in a relatively short time. Let's start in 1975. Our time rate is 5 seconds per year. This seems more complicated than proper motion alone. In order to understand what we're seeing here, let's mark the point with the proper motion of Vega. The star appears to orbit around this point, revolving exactly once a year. This motion around the green mark is an illusion caused by the Earth's revolution around the sun. The effect is called parallax. If we could observe Vega from the sun, it would appear always at the center of the green mark, moving with the proper motion. The parallax confirms that the Earth moves around the sun. The length of this line represents 1 second of arc. So the angles involved are very small and must be measured with great care. But once the parallax has been measured, we can find the distance to the star using simple geometry. Vega turns out to be 25 light years away. Let's look at the motion of another star for comparison. Here, in a group of stars called the Hyades, recognized by their V-shaped pattern in the sky, is the star Aldebaran. We're going to magnify Aldebaran 30,000 times as we did Vega. Again, we start with 1975 and set our time rate at 5 seconds per year. Aldebaran has less proper motion than Vega. The green mark moves with proper motion alone. The parallax is smaller, and the star appears to move back and forth along a line. The appearance of parallax depends on the star's location in the sky with respect to the plane of the Earth's orbit. Aldebaran lies almost in this plane, while Vega lies in a direction more nearly perpendicular to it. The parallax indicates that Aldebaran is 65 light years away, about 2.5 times further than Vega. Let's watch the motions of stars in some particular directions. Here we see stars down to 8th magnitude. The region includes the constellations of Lyra and Hercules, upside down from this angle. The green cross marks the point in the sky toward which the sun is moving. Let's watch the proper motion of these stars looking straight ahead as we go forward in time 200,000 years. Now from 200,000 AD back to the present. During this enormously speeded up motion, we drifted with the sun into this cloud of stars and then backward. The proper motion tells us which direction the sun is moving. If we look sideways, perpendicular to the sun's motion, we can see the constellations of Andromeda and Triangulum. Again, we'll move 200,000 years into the future. Each star has its own particular velocity as the sun glides through space. Now let's look backward as if out of a rear window. This is the star pattern of 100,000 years ago. From these unique vantage points, and moving thousands of years through time, we can see the effects of two quite different kinds of motion. The Earth revolves around the sun, producing parallax, and the sun drifts through the stars that surround it.